And so those ideas led to this notion that's now called cosmic inflation, that in the earliest moments, the universe wasn't only expanding, as it is indeed still doing today, but it might have been speeding up in its expansion. It might have been rip-roaringly fast expansion, exponentially quickly. And that could have been driven by energy that was kind of temporarily locked up in some sort of exotic particles, like the Higgs particle, or things kind of like the Higgs particle that have since been found experimentally. And if the universe went through this very short but extremely violent phase of exponentially fast expansion, this inflation, then that could both shore up a number of these kind of shortcomings or puzzles or paradoxes about the regular Big Bang model, and also lead to a whole host of new questions and new predictions for things one astronomer should hopefully then be able to see and detect observationally. And then it took a long time. It took more than 10 years since then before the first observations could sort of catch up and start detecting things like the very subtle pattern of bumps and wiggles in the distribution of the earliest light that astronomers can detect, something called the cosmic microwave background radiation. Light that was, in some sense, kind of remnant heat, a remnant glow from that very violent early phase of the Big Bang. And there's a very specific pattern of what physicists call fluctuations, little parts where some parts of the sky look slightly hotter and other parts look slightly colder, slightly more energetic, slightly less energetic than average, just by 1 part in 100,000. Very minute little bumps in the distribution of matter and energy across the entire universe. Those bumps are predicted by inflation. In fact, the pattern of those bumps have been predicted by many models of inflation, and that they now match the latest observations to extraordinary accuracy. So it looks like, hey, we're done. We have one universe. We've explained that one universe. And part of what people began to realize early in this new set of studies is that once this phase of inflation starts in one patch of the universe, it will likely keep going forever. It became known as eternal inflation. So within one little bubble, one island in which we would ultimately find ourselves living, inflation will sort of will self-consistently come to an end. One can understand why our patch of space isn't expanding the way it certainly seems to have or is predicted to have in that earliest moment. But instead, while our little patch, our little island, our little suburb of the cosmos has stopped expanding exponentially, neighboring parts, so this theory seemed to suggest, we keep on expanding exponentially quickly, and so some part of space would always be growing. So once inflation starts somewhere, it seems, at least according to these equations, these calculations, inflation will never end. It's eternal, at least is thought to be eternal. So that raises a whole host of questions, because now there could be ultimately an infinite number of these bubbles, of these seemingly independent little universes, from the inside of which they look enormous. It's our entire observable universe and much more that we're talking about. And yet if seen from a different perspective, so these theories now suggest, there could be an infinite number of these parallel bubbles that are constantly kind of roiling up out of nothing, out of a vacuum, and expanding and going through a kind of Big Bang-like evolution all their own. So now the question becomes, how typical are any things that we want to calculate about our own universe? We want to describe the phenomena we see. If we can't determine the outcomes, we want to at least give quantum mechanical probabilities. How likely should we see this event or that event? And probabilities needs what physicists call a measure. You need to know, in some sense, baselines for how to calculate how likely an event would be or otherwise.
So, for example, you mean how likely our universe would be amongst all these other universes?
Well, we got stuck there because we first wanted to ask how likely is it for this table to hold together, say. And ultimately, if we push our equations back, we then have to ask, as a prerequisite to answering that question, it seemed, we also suddenly have to ask how likely is our universe to have been created and gone through the sort of evolutionary history that we've observed. And somehow it looks, at least to some physicists, like answering questions about 2 electrons dancing on this table today suddenly seem subject to this big, crazy, ungainly, unanswered question of how likely is our own universe. And that gets a lot of people very uncomfortable, understandably uncomfortable.
So what makes people a little upset about the multiverse, yeah, we should ask that question, which is also related to the nature of reality and how much we can probe, right, of what's out there, is the fact that if you believe that there are other universes outside our universe, right, that implicitly means that we cannot directly probe them. And there is a problem here, from a physicist perspective, right? Because if you cannot test your hypothesis,
Right.
what are you doing?
Good. No, I agree. And so that doesn't mean it's an illegitimate question. It is, we might say, a philosophical, metaphysical question. And those are important questions. Some of the most important ones that humanity's asked, I think, fall in that bin. So I don't think that's a taint. I think, I like to turn it around, maybe my glasses, my glasses half full. But like I said, we've developed great tools with which to even broach those questions. That doesn't mean we have the answer yet. But I agree. Now, there are proposals, again, as you know. Some people wonder, if these really are separate bubbles. I tend to think about the multiverse as like a big bathtub. And like in a bathtub, you can have lots of bubbles. And sometimes in a real bathtub, some bubbles will coalesce. I mean, this is something you've studied in detail, right, for a long time. And maybe that happens even in the multiverse. If the rate at which new universes get made, so to speak, nucleate, if that rate's large enough, then it's not impossible to imagine bubble universes colliding. Not every universe will collide with every other, but there could exist collisions, some likelihood of some collisions. And if so, then that could possibly show up as some very subtle signal, for example, in the cosmic microwave background radiation. I don't think that's particularly likely, but at least it gives a little handle. And some people, like Roger Penrose in a slightly different context, have tried to look very hard to say, not just is that possible, does it show up in this current cornucopia of data? So I wouldn't say it's in principle never ever testable. They might not be strongly testable. They're certainly not sort of where we can say with great confidence that's ruled in, that's ruled out. But there are clever ways, fun ways to think about possible inroads empirically. And otherwise, like I say, I'm perfectly comfortable saying these are metaphysical questions that we're led to for good reasons that we have confidence in. We have tools with which that we've sharpened over a long, long time that we can at least try that next step. But I don't think that we sort of have to stop doing physics and cosmology until we figure that out. That's where I think some of the critics maybe take it a bit too far.
No, that's true. No, that's definitely not the right approach.